I thought we could talk a little bit about digital twins today, just because it's a sort of buzzword that's been about and been around the blocks a little while, and you may have heard of it. And it's not entirely clear, right? Immediately, is it really a new, relevant, important thing? Should I care about it? What is it even?
Is this just a new cloud?
Is it exactly? Is it just the new cloud? Is it new, or is it just sort of old wine in new bottles, as it were?
Digital twins similar to simulation, isn't it?
Simulation is not an unimportant thing in digital twins, but it's perhaps not the first thing to think about. I think it's worth perhaps looking a little bit, and maybe I'll sort of try and sketch something out there, and then we can sort of start talking a little bit about, is it just simulation or what's going on there? You ask 7 experts on digital twins, you'll get 10 different definitions of what a digital twin is. I'm not even going to go there, right? I'm going to try and keep this really simple and fairly high level, and just sort of try and work out what are sort of the key components. And the biggest 2 components really are that we have some sort of actual real world system, which I'm going to put here. It could be anything, right? It could be a bridge, it could be a human, it could be an organization, it could be a car. And then what we do in the digital twin setup is we create a digital representation of that real system. We have a digital twin over here. And the digital twin, as the name implies, is a digital artifact. So it's not something in the real world, it's something that lives in the computer. And depending on what our real system is, the digital twin might just live on a little desktop PC somewhere, or it might require quite a significant sort of cloud style deployment somewhere, depending on what we want to do, right? I mean, there's some people who talk about building a digital twin of Earth. That's probably not going to fit on the desktop. You'll probably need a fair amount of compute for that. If it's a digital twin of my cup of tea at home, which I've built maybe for the fun of it, then maybe I've run that on a little Arduino or something. The important thing is it's connected to this real system. It's connected in 2 ways. We need sensors on our real system, and the digital twin uses those to learn about the state of the real system. So it tries to work out what's happening in the real system, and so that it can maintain a sort of continually up-to-date representation of the real system. And that doesn't mean it's millisecond to millisecond accurate. How accurate, how often it gets data from those sensors, depends really on what we actually built the digital twin for, and we'll get to that in a moment. The other thing that a digital twin typically has to have is it has to have some way of affecting the behavior of the real system. So the real system has to provide some ways of changing it, and the digital twin will use those effectors to make changes. Now, if that is a digital twin, say, of a car engine, then typically there are little ECUs, etc., little control devices built into the car engine that allow the computer systems of the digital twin to talk to those little control units, and they can then make adjustments to the amount of gas that's being injected, or the amount of air that's or whatever other aspects of that system. For other systems, these effectors may need to be more complicated things. And again, if we look at, say, for example, organizations, etc., as our real systems, then these effectors can become really complicated really quickly, because they really then maybe are about having a human decision maker in the loop somehow, who then tries to actually make change in the organization based on something they've learned from the digital twin, rather than something more direct, like a sort of very closed loop control system. The reason why we built this, really, and that's the important thing, is because we want to be able to provide additional services. We've learned, I think, over the last 50, 60, 70 years or so, that computers are really good at keeping track of things. They're really good at helping us plan things and sort of doing what-if analysis, doing calculations, and so on and so forth. But of course, they can only do that if there's something in the computer to manipulate and to track and to plan over, etc., right? So they need a representation of things in the real world. And if I have a bridge, like Waterloo Bridge down the road, and I want to maintain that effectively, and the digital twin is about bringing enough information of the real system into the computer, building a model effectively of the real system in the computer, so that the computer now is able to do analysis on top of that, make plans, provide the decision support, or even make decisions and apply them back to the real system in some way. And so that's where the value of the digital twin is. You started out early on, I think, and you sort of said, isn't that just simulation, right? And it's lots of things in a way, right? We could equally ask, isn't that just modeling? You could equally ask, isn't that just AI? Isn't that just data science? Isn't that just control systems? Isn't that just SCADA, right? There's lots of these things that are seemingly doing similar things, or I would argue perhaps are doing part of this.
What seems to be different here is those connections. You mentioned sensors to send data.
So that's one. I think that's one thing. There are these differences. Although, especially if you look at things like control systems, they kind of have that as well, right? Or adaptive systems, they kind of have that kind of notion as well. There's I think partly a difference in scale. There's a difference in the capabilities that we typically would then put into these services in our digital twin. If I go back at the sort of starting point of is this just a buzzword? Is this really something new? I guess the answer is yes and yes, right? So yes, of course it's a buzzword because all of the components and building blocks are there. We know how to build simulations. In fact, we know how to build simulations that keep up with the real world. We know how to do data science and data analysis, and we have a good idea nowadays of how to do a lot of AI stuff. But what I think is new is that this makes an emphasis on bringing all these things together in an engineered system that represents something in the real world and allows us to manage that something. And I think that to me is where the value is, and that to me is also where the challenges are. Because it's not immediately obvious. How do you engineer these kind of complex software systems at this scale? How do you bring complex concepts and ideas like simulation, like AI, like data science, data processing, data cleaning, like control systems together in a safe and robust and assurable way that's manageable by the humans developing it, that can live a very long time, right? If you imagine this is a digital twin of a bridge, again, that bridge is going to be there for hopefully, tens, hundreds of years. It'd be great if the digital twin could kind of live alongside it for that period of time as well. But actually, also, the bridge is going to change. What we want of the bridge is going to change over that period of time. The kinds of things that we therefore want to do with the digital twin are going to change over that period of time. And arguably, we don't know at this point how to build those sorts of systems that are able to manage a huge amount of data about something in the real world, adaptively allow flexible decision support or decision making over that system over long periods of time, and do that in a world where everything around that real world system also has a digital twin that also has ideas of how to manage its part, and ideally should work. All of these guys should work together as well. Okay, so what's really happening in here, right? Because I've sort of tried to make this point about how different disciplines are involved, but obviously I've been a bit hand-wavy about this. So maybe if we open up this sort of digital twin box here for a moment, we can perhaps see that a little bit more. So let's see what happens in that box, right? In principle. So if I draw sort of a big box here for our digital twin, then what goes into this, right? So we've said it goes and says, well, which side? I'm going to draw this way around. It has various sensors, and we've said eventually we'd like it to do things, okay? So it has to have those effectors. But what happens between this and that? Okay, and what happens between this and that is a number of steps, right? So we get this data in here. So we've got lots of data, and data are really just numbers, okay? Those numbers, they need cleaning up, right? Because sensors are fallible. They might not always give me data every time step I'm asking for them, or the data might not be accurate. In fact, the real world might be outside of the range that the sensor can handle. But also, I've got multiple different sensors, and I kind of need to stick them together, right? So there's lots of processing that needs to happen. So I've got a sort of initial, just sort of kind of data cleaning, pre-processing, I'm going to call it, where the data is brought in and is cleaned up to a standard where we can start doing stuff with it. Okay. The next step, we need to try and understand what that data means. And so we're going to do what's called analysis, right? What we could call analysis. And that really turns data, if you will, into information, into knowledge and information. And what we do there is we may combine different data sources or different sensors. But also we will perhaps already have some built-in knowledge in our system here, in our digital twin, where we kind of know, for example, we have maybe if this is a digital twin, say of an aircraft engine, we might have a model of the physics involved in the aircraft. So that helps us make sense of the sensor data by saying, oh well, if that temperature sensor is at that value, then I can predict that over here in the engine something interesting is happening, right? Or I would expect that sensor value to be in that kind of range, and then if it isn't, then that's an indication that maybe something has gone wrong, right? And that's only possible because I have some knowledge about the thing that I'm monitoring that allows me to expect certain things, or that allows me to infer certain things from the data that I've collected. Okay, so at the end of this, really what I come out with is a sort of up-to-date model of the real system. That's what comes out really of the analysis phase. And what's fed into this is the data that we collected from the sensors, which is kept in some sort of knowledge model in my digital twin. That's also fed into this analysis that allowed me to make the analysis in the first place. What I'm going to do with this model next is I'm going to I've look at it and I go, okay, maybe I just present it to somebody so I can see it, and that's one of the possible services I might provide, right? Is I present this to somebody and I say, okay, this is the state of your aircraft engine, this is the state of your healthcare emergency department, or this is the state of your car or your bridge, etc. Great, here you are, right? That's the first thing I can do. Some people call that a digital shadow because it doesn't actually do anything through the system. It just shadows what the system does. But I can do more potentially, right? I can do what-if analysis at this point. I can do scenario planning, etc. And I would do that perhaps if the analysis here tells me that something is not quite right. Maybe the system doesn't quite run optimally, or I've spotted a problem, something unexpected in my data, etc. And so then I would do some form of what we call planning, really, I guess, at that point, right? So it's, for example, what-if analysis. So what-if analysis typically is, if I make this change to the system, what might happen? Right? And that's particularly interesting if I have a digital twin, say, of a socio-technical system, so where there's people and technology involved, say, one example might be an emergency care department, where I don't want to go in and just go, oh, right, from today, we're going to do everything differently. That probably wouldn't be a good idea. So instead, what I can do is I can say, okay, I've got a really good model of how my emergency department works. I've got a good understanding of that. I've got data that comes in. I've analyzed this. I've got a reasonable representation. I've got some knowledge about maybe the workflow processes, etc. Now, what if I made an adjustment to the work processes? Or what if I used a different tests from a different provider, perhaps, to check for a particular illness or something like that, right? What might the outcomes be? And I can analyze that. Typically, that's where simulation comes in. I would analyze this to sort of run it in different contexts, right? I might say, okay, if I do this, what happens under normal conditions? What happens if my emergency department suddenly is overrun by patients? What happens if half of my staff are ill? And I can really try and explore that. And obviously, yes, it's all in the digital and the virtual, and it's all sort of at one remove from the real system. And so I need to take that into account when assessing the results from that. They might not be a totally accurate reflection of what happens in the real world, but they will give me an indication of whether this is a sensible thing to try and do or not, right? Equally, if this is say a digital twin of an aircraft engine, again, I might want to say, okay, something's weird's going on. Based on my knowledge of the physics and the data that I have about the current state, what if I injected more fuel, or did that or that, and I can sort of try out different scenarios. There, hopefully, I then do a sort of more automated decision making that then might actually directly affect the engine rather than just providing it as a decision support system, right? And so that's sort of what if analysis is one of the things I might do here. I could do forward planning. I could sort of try and sort of do problem solving of that sort of thing. The Mars rover might do something like that, where it finds itself in a situation that doesn't quite match the expectation from the mission planning, and it kind of has to go, right, there's a stone here, I can't go straight, what do I do? Right? And then it needs to work out where it goes. Again, it needs a digital representation of itself and its environment to be able to do that, and that's a digital twin. And then eventually, hopefully, we'll get to some sort of decision making that allows us to say, these are the changes that we're actually going to implement. And again, in the sort of digital twins, as they come from the manufacturing world and from the sort of aircraft management and car management and so on world, this we would want to be automated fully. So we'd want to be able to go around this cycle fully and it just having a direct effect. But there's nothing wrong with digital twins of, say, socio-technical systems, etc., where this decision making might actually be done by a human, and then lead to changes in policy or changes in workflows or changes in the sourcing of equipment and so on. But again, I think the key thing here that you can see is that there's all kinds of different disciplines involved, right? We've seen all of this over here is all about data science and data analysis. We've seen here some aspects of sort of extracting knowledge from data, which is very much the sort of realm of AI, isn't it? We've seen this sort of planning stage, well, we've seen this modeling stage, knowledge models, and these models in the middle here, which is really about knowing how to build models. These could be knowledge graphs, but they could also be more typical sort of engineering type models, right? And then we come to the planning stage, which again could be some AI component that goes into there, or it could be simulation components, and again needs that expertise. And then decision making is about understanding the results of that, but also about knowing how to translate that into signals to be sent to the various effectors that we actually have available. Okay, and so all of these things have to come together to build to build a digital twin, and they have to come together in a controlled and systematic way, where ideally we're also able to afterwards say, we're okay with relying on that digital twin. We've built it to a sufficient standard of quality where it's not scary, but it's actually a useful thing.
No matter what the system is, it's difficult to get it to be, what am I trying to say, not accurate, but as complicated. Even your cup of tea, I remember high school chemistry and Brownian motion. How do you decide to what granularity?
Right. Yeah, I think that's a really good question, right? And it's a really important question, because I think one fallacy I'm always tempted to say in some sort of descriptions of what a digital twin is I think some people call it an identical digital representation or like for like or things like that. And of course that's not right. That's fundamentally impossible. But even if it were possible, why would we? Right? If we just want something that's absolutely identical, we have the real thing. Why not just use that? Right? The point of the digital twin is that we have now a virtual representation that we can manipulate more easily and analyze, etc., more easily, but also that it's focused on the things that we're actually interested in. Okay, so take the example of the bridge again. Waterloo Bridge. I'll be interested in maintenance perhaps for that. Okay, so I need to probably know something about the materials from which it was constructed, and I need to have some physics knowledge around that. Okay, it's probably going to be useful to have a bit of data about its usage. So how many people walk over it, and maybe even on average how much they weigh, so like get a bit of a sense for the sort of load that it carries that way. Equally with the cars, right? How many cars and how much, how many buses versus how many SUVs versus how many minis, I think is probably a useful sort of information. And I probably don't just want that as a sort of one number average, but I probably want some sort of time series data about that. It may even be interesting to know a little bit about, say, The weather in particular, I might not care so much about how much it rains, because I'd probably assume that maybe that isn't the biggest impact on the decay, but maybe I'd be interested in knowing whether there's any heavy storms that have affected the bridge, because that may have more of an impact. But again, maybe I find out actually, I'm not at all a civil engineer, so it's entirely possible that Waterloo Bridge, you'd kind of go, as a civil engineer, kind of go, it really doesn't matter how much it storms, so I don't care about that information. And then you leave that out, right? Everything you can leave out is a good thing, but you don't have to manage it. We've talked about Waterloo Bridge, right? Exists for, I don't know how long it's been standing there, and hopefully it's going to be standing there for another however many years. So that digital twin needs to live alongside it. Over time, I might say, actually, I thought the wind isn't important, but it turns out, especially with climate change, strong wind events have become more frequent, and I've noticed that does seem to have an effect on the bridge. So it probably would be a good idea to be able to include that in my analysis. Now what do you do, right? Well, one thing is easy, right? Well, comparatively easy. You can say, okay, well, I'm going to build an extension of my existing digital twin, and from now on, we're going to collect data about the weather, and we're going to include that in our analysis. But then what about all the storms that Waterloo Bridge has seen before you did that? Should you care about those as well? And if so, how do you do that if you haven't collected that data because you didn't have the sensors? So then you can bring in historical weather data and you can start building up approximations. But you've got to build additional complexity around that at that point, right? And so I think one of the things that, again, the digital twin idea, none of this is new in some ways, right? But what the digital twin idea brings is it sort of focuses in and says, actually, when we build these things, these are all concerns that we have to somehow bring together and align and make work together and really think through as we engineer the system. We've got to work out what's the minimum data that we need to collect, both for our needs now and for meaningful future needs. But we don't want to collect too much. We've got to work out what granularity do we collect that data at? When do we throw it away? Because really you can't keep all of that data about even just about Waterloo Bridge forever, right? I mean, that's just very quickly that just becomes ridiculous. So there's lots of these sort of engineering questions that suddenly pop up just because the idea of digital twins is about taking all of data science and simulation and AI, bringing them together to focus on real world objects on a continuous and sort of long-term adaptive basis. And that's where it becomes interesting, I think. Various places, it doesn't have just hard-coded text, but it puts in text that it copies out from the model, right? So it'll go into those. Don't
need to worry about the difference too much. If your loop or your function does the same thing repeatedly with only minor variations, this will be very effective.